The night sky suggests stillness. Stars return to the same positions. Galaxies hold their shapes. Nothing appears to shift in any meaningful way. But that impression depends entirely on how motion is measured. When astronomers compare the Milky Way's position against the deepest available reference, they find something unexpected. Our galaxy is not only moving outward with cosmic expansion, it is drifting in a specific direction at a measurable speed alongside thousands of other galaxies doing the same. This motion is not explained by anything nearby. It cannot be traced to a single visible object, and it does not emerge from random chance. The evidence does not arrive as an image. It arrives as imbalance, as temperature differences across the sky, as coordinated movement spread across distances so large they resist intuition. Gravity revealing itself through consequence rather than appearance. What stands out is not how fast this motion is, but how consistent it is. Direction exists where symmetry is expected. Influence appears where visibility ends. Something massive is shaping the flow of galaxies, quietly and persistently, from a region of space that remains difficult to observe directly. Welcome. If you enjoy calm explorations of real science and the quiet strangeness of the universe, consider liking the video and subscribing to the channel, and let us know where you're watching or listening from tonight. Wherever you happen to be, drifting through space along with the Milky Way. Motion is not something the universe occasionally does, it is what the universe is doing all the time. Nothing that exists on cosmic scales is truly at rest. Stars orbit the centers of galaxies. Galaxies move within clusters. Clusters drift through vast networks of structure that stretch across hundreds of millions of light years. Even the space between these objects is changing, expanding steadily, carrying everything along with it. Stillness, when it appears, is always a matter of perspective rather than reality. And yet, when looking up at the night sky, motion feels absent. The stars seem fixed. The familiar patterns return year after year with reassuring reliability. The Milky Way arches overhead like a painted backdrop, not like a river in motion. This illusion is powerful because the movements involved unfold on scales of distance and time that sit far outside everyday experience. A galaxy can travel enormous distances over billions of years and still appear frozen during a human lifetime. This contrast between reality and perception shaped early ideas about the cosmos. For much of history, it felt natural to assume that the universe, at its largest scales, was fundamentally stable. Objects moved locally, but the grand structure itself seemed permanent and unmoving. Even as astronomy improved and more precise observations became possible, that assumption lingered quietly in the background. Early gravitational thinking, rooted in classical mechanics, reinforced this intuition. Gravity was understood as a force acting between objects with mass, pulling them toward one another across space. It worked beautifully for planets, moons, and falling objects on Earth. Motion was something that happened when a force was applied, and rest was the default state once forces balanced out. In that framework, motion always had a cause that could be pointed to, and an outcome that made sense. An apple falls until it hits the ground. A planet orbits until its path settles into a predictable loop. It took time to realize that this way of thinking becomes less reliable as scales increase. On cosmic distances, there is no meaningful ground to hit, no fixed background against which motion can easily be judged. A galaxy can move forever without ever arriving anywhere in particular. There is no universal marker that says a journey has begun or ended. Motion exists without a clear destination, and gravity does not always resolve itself into neat closed patterns. Galaxies appear fixed largely because their motion is smooth, shared, and slow relative to human perception. The Milky Way does not streak across the sky like a meteor. It glides, embedded within a larger flow of matter that includes neighbouring galaxies and distant clusters. From within that motion, everything nearby seems stationary, much like passengers on a calm flight feel at rest until they glance at the ground far below. Astronomers learn to recognize this illusion by abandoning the idea that motion must be obvious to be real. Instead of asking what appears to move, they asked how motion could be detected indirectly. This shift marked a turning point. Motion became something inferred through comparison, measurement, and subtle imbalance rather than direct visual change. One of the most important realizations was that speed alone does not tell the full story. At large scales, direction becomes far more meaningful than raw velocity. A galaxy moving quickly in a random direction tells a very different story from thousands of galaxies moving together along a shared path. Direction implies structure. It suggests influence. It hints at something shaping motion from beyond the immediate surroundings. This is where intuition begins to struggle. Everyday motion usually has an endpoint. A car travels to a destination. A thrown object follows an arc and comes to rest. Even orbital motion feels complete, repeating endlessly along the same track. Cosmic motion often lacks this sense of closure. Galaxies drift without arrival. They respond to gravity without ever settling into final positions. The universe does not seem interested in finishing what it starts. That unsettles the human mind in subtle ways. There is comfort in destinations, in the idea that movement leads somewhere definite. Motion without an endpoint feels unfinished, even purposeless. But in cosmology, motion does not require intention or conclusion. It exists because mass exists, because gravity operates across vast distances, and because space itself evolves over time. Scientists began to frame motion not as a narrative with a beginning and end, but as evidence. Motion becomes a clue. It reveals where mass is concentrated, how space is structured, and how the universe has evolved from earlier states. Even when the cause of motion cannot be seen directly, the motion itself remains measurable and meaningful. This approach transformed the way astronomers thought about unseen influence. If objects move together, something must be guiding that movement, whether or not it can be photographed. Gravity does not announce itself with light. It leaves its mark through acceleration, through distortion, and through shared trajectories that persist over immense distances. There's a quiet elegance to this idea. The universe does not need to explain itself visually in order to be understood. Patterns emerge from careful measurement, from patient comparison, and from the willingness to accept that some of the most important structures are known by their effects rather than their appearance. At the larger scales, motion becomes a kind of language. It tells scientists where matter lies, how strongly it pulls, and how different regions of space relate to one another. It also reveals when existing explanations fall short. When motion refuses to align with expectations, something new is being indicated, even if it cannot yet be named. This is why direction matters more than speed. Speed can increase or decrease for many reasons. Direction, when shared across vast regions, points toward deeper structure. It suggests coordination where randomness might otherwise be expected. It hints that the universe, while not designed, is far from disordered. The Milky Way participates fully in this reality. It is not an anchor point. It is not a center. It is one moving component within a much larger pattern. Its motion is gentle, persistent and revealing, even if the cause of that motion remains difficult to isolate at first glance. Understanding this requires letting go of the expectation that motion must feel dramatic to matter. Cosmic motion is subtle, slow, and deeply cumulative. It unfolds over timescales that make human history feel fleeting. Yet it shapes the largest structures in existence and determines how galaxies relate to one another across the observable universe. By learning to read motion as evidence rather than spectacle, astronomers opened the door to discoveries that could not be made by light alone. They learned to trust patterns that emerge only when patience replaces immediacy, and when direction is valued over destination. The universe is not still. It never has been. And once that idea settles in, the absence of a visible endpoint stops feeling like a problem. Motion itself becomes the signal, quietly pointing toward influences that wait to be understood. The idea that the universe is expanding did not arrive gently. It arrived by quietly overturning expectations. In the early 20th century, astronomers were still debating the scale of the cosmos itself. Many believed the Milky Way might be the entirety of the universe, with faint spiral shapes seen through telescopes interpreted as nearby clouds of gas. Motion was observed, certainly, but it was assumed to play out within a largely stable cosmic setting. That assumption began to unravel through the work of Edwin Hubble. Working at the Mount Wilson Observatory in the early decades of the 20th century, Hubble studied distant galaxies and noticed something subtle but persistent. The light from most galaxies was shifted toward the red end of the spectrum. This redshift indicated motion, specifically motion away from the observer. More striking still, the farther away a galaxy appeared to be, the faster it seemed to be receding. From this pattern emerged what became known as Hubble's law. In its simplest form, it states that the farther away a galaxy is, the faster it is moving away from us. Not because we occupy a special position, but because space itself is stretching. Every region moves away from every other region on average, and distance determines the rate. Put plainly, the universe is not expanding into something. It is expanding everywhere, all at once. Galaxies are carried apart as space between them grows, much like dots on the surface of an inflating balloon. No single dot is the centre, and none is responsible for the motion of the others. This idea reshaped cosmology almost overnight. Expansion provided a clean, elegant framework for understanding large-scale motion. It predicted that galaxies should, on average, recede from one another in a smooth and orderly way. Direction shouldn't matter. From any vantage point, the universe should look roughly the same, with galaxies moving away evenly in all directions. This expectation of symmetry became foundational. If expansion dominated cosmic motion, then deviations should be small and local. Nearby gravitational interactions might cause minor departures, but over large distances everything should average out. Expansion promised simplicity at scale. To make sense of this, astronomers leaned heavily on the concept of cosmic averages. Individual galaxies might behave unpredictably, but when thousands or millions are considered together, their motions should reveal underlying order. This statistical approach allowed scientists to smooth out local noise and focus on the grand pattern. Out of this mindset grew observational cosmology, a discipline defined less by individual objects and more by populations, surveys, and trends. Instead of studying one galaxy in detail, astronomers began mapping thousands, measuring their distances, velocities, and distributions. Meaning emerged not from singular cases, but from collective behavior. Velocity surveys became essential tools. By measuring how fast galaxies appeared to be moving away or toward us, astronomers could test whether expansion alone explained the data. These surveys required patience and precision. Distances had to be estimated carefully, redshifts measured accurately, and biases accounted for. The work was methodical, often unglamorous, and deeply statistical. At first, the results seemed reassuring. On the larger scales, expansion did dominate. The universe behaved broadly as predicted. Galaxies far away receded faster than those nearby. The pattern held up across different directions and different regions of the sky. But as data improved, small irregularities began to stand out. Some galaxies were moving slightly faster or slower than expansion alone would predict. Others showed subtle directional preferences. At first, these deviations were easy to dismiss. Measurement errors were common, distance estimates uncertain, and local gravitational interactions messy. No one expected perfect alignment with theory, yet the deviations did not disappear as datasets grew. Instead, they became clearer. What made this intriguing was not the existence of irregular motion, but its coherence. Deviations were not random. They appeared structured, shared across groups of galaxies, and aligned over surprisingly large regions of space. When averaged carefully, certain directions showed consistent residual motion that expansion alone could not erase. This posed a quiet challenge. Expansion explained most of what was seen, but not all of it, and because expansion set such a strong baseline expectation, anything that deviated from it became especially informative. The very success of the expansion model made its shortcomings easier to spot. Expectations play a powerful role in interpretation. When scientists expect symmetry, asymmetry becomes meaningful. When smooth motion is predicted, coordinated deviation stands out sharply. In this way, Hubble's law did not just explain cosmic motion. It sharpened the tools needed to recognize when something else was at work. The cracks were subtle at first, almost polite. No single observation demanded a rethink. Instead, tension accumulated slowly, across surveys, across decades, across improvements in instrumentation and methodology. The universe was behaving mostly as expected, but not entirely. Astronomers responded the way they always do, by measuring more carefully. Larger surveys were conducted. Different wavelengths were used. Independent teams repeated analyses. The goal was not to overthrow expansion, but to understand its limits. What emerged was a layered picture. Expansion governs the overall behavior of the universe, setting the broad flow of galaxies apart from one another. On top of this flow, however, sit additional motions, smaller in magnitude but rich in information. These motions carry signatures of gravity, structure, and mass distribution that expansion alone cannot account for. The elegance of expansion remained intact, but it was no longer complete on its own. The universe was not simply expanding, and nothing more. It was expanding and responding to gravity at the same time, producing patterns that only become visible when expectations are carefully defined. This is where cosmology grows interesting. Not in the confirmation of clean theories, but in the moments where reality gently refuses to fit perfectly. Expansion sets the stage. Deviations reveal the actors. By establishing a clear expectation for how the universe should behave on average, astronomers gave themselves a powerful reference point. Against that backdrop, motion stopped being noise and started becoming signal. Directional drift, shared velocities, and coordinated departures from symmetry could now be treated as evidence rather than inconvenience. The universe, it turned out, was not violating expansion. it was layering something on top of it. And once that possibility was taken seriously, motion ceased to be just a consequence of cosmic growth. It became a diagnostic tool, quietly pointing toward influences that expansion alone could never explain. As astronomers refined their measurements, it became clear that expansion alone did not describe everything that was happening. Galaxies were broadly moving apart as space expanded, but layered on top of that smooth motion was something else. A quieter, more local movement that refused to average away. To describe this extra motion, scientists introduced the idea of peculiar velocity. Despite the slightly awkward name, peculiar velocity is a simple concept. It refers to the motion of a galaxy relative to the smooth expansion of the universe. If expansion sets the baseline for how fast a galaxy should be moving away due to the stretching of space, peculiar velocity is whatever motion remains once that baseline is removed. An everyday analogy helps. Imagine standing on a long moving walkway at an airport. The walkway carries everyone forward at the same steady pace. That shared movement is like cosmic expansion. Now, imagine someone walking briskly along the walkway, either faster or slower, perhaps even turning slightly to the side. That extra movement is the peculiar part. Both motions happen at the same time, and neither cancels the other. In astronomy, separating these motions relies on redshift measurements. When light travels through expanding space, its wavelength stretches, shifting toward the red end of the spectrum. This redshift allows astronomers to estimate how fast a galaxy is receding due to expansion. By combining that information with distance measurements, scientists can calculate the velocity expected from expansion alone. Once that expected value is known, it can be subtracted from the galaxy's observed motion. What remains is the peculiar velocity, the part caused by gravitational influences rather than the growth of space itself. This correction process is delicate. Distance measurements are notoriously difficult, and small errors can propagate through calculations. Early on, this made astronomers cautious about overinterpreting results. Even so, patterns began to appear. Some of the earliest systematic galaxy velocity measurements came from work carried out at Mount Wilson Observatory in the first half of the 20th century. Astronomers there compiled catalogues of galaxy redshifts and distances, gradually assembling one of the first large-scale views of cosmic motion. These data sets were limited by modern standards, but they laid essential groundwork. When researchers corrected these early measurements for expansion, they expected the remaining velocities to look messy and random. Local gravitational interactions, such as galaxies pulling on their immediate neighbours, should create a kind of cosmic jitter. Over large areas of the sky, those effects should cancel out, leaving no preferred direction. That is not what the data showed. Instead of scattering evenly, the residual velocities showed signs of alignment. Galaxies in certain regions tended to drift in similar directions. Groups of galaxies shared motion that could not be explained by expansion alone, and this coherence extended farther than local gravity should allow. At first, skepticism was the sensible response. Small datasets are prone to bias. Measurement uncertainties were large. Distance indicators were still being refined. It was entirely possible that the apparent patterns were artifacts rather than physical effects. To test this, astronomers did what science does best. They gathered more data. As galaxy surveys expanded and techniques improved, velocity catalogues grew dramatically. Larger samples reduced random noise and made systematic effects easier to identify. If the peculiar velocities were an illusion, they should weaken as more galaxies were added. Instead, the opposite happened. The pattern strengthened. Statistical analysis showed that the alignment of residual velocities was extremely unlikely to arise by chance. The probability of random motion producing such coherence dropped as sample sizes increased. What had once been tentative hints became statistically robust features of the data. This was a turning point. Peculiar velocity stopped being treated as a nuisance or correction term, and started being treated as a signal in its own right. It was no longer something to explain away. It was something to understand. Another crucial insight followed soon after. Peculiar velocity behaves differently depending on scale. On small scales, motion is indeed chaotic. Individual galaxies can move unpredictably as they interact, merge, or pass close to one another. In these environments, peculiar velocity looks exactly as intuition would suggest, messy and irregular. On larger scales, however, the chaos fades. When astronomers examined entire clusters and superclusters, they found that peculiar velocities became smoother and more coherent. Large groups of galaxies drifted together, sharing a common motion across tens or even hundreds of millions of light years. Local disturbances averaged out, revealing an underlying flow. This scale dependence was a powerful clue. It suggested that peculiar velocity was tracing something fundamental about the universe's structure. Gravity does not operate randomly. It responds to how mass is distributed. Where mass is spread unevenly across large volumes, it creates large-scale motion. In this context, galaxies are not independent actors. They behave more like test particles, responding to the gravitational landscape they inhabit. Their peculiar velocities reveal the shape of that landscape, even when much of the mass involved cannot be seen directly. This reframing had profound consequences. Instead of asking why a particular galaxy was moving the way it was, astronomers began asking why entire regions moved together. Peculiar velocity became a tool for mapping invisible mass, much like a breeze reveals the presence of air by how leaves move. There was also a philosophical adjustment. Expansion had encouraged the idea that the universe should look the same in every direction on large scales. Peculiar velocity introduced a controlled way to talk about departures from that symmetry. The universe could still be uniform on average, while containing large regions of coherent motion driven by structure. Importantly, these motions were modest in speed. Peculiar velocities are usually small compared to the velocities caused by expansion at great distances, but their significance lies not in their magnitude but in their coordination. A few hundred kilometers per second, when shared by thousands of galaxies, carries far more information than a dramatic but isolated movement. This period in cosmology rewarded patience and restraint. Peculiar velocity cannot be photographed. It emerges only through careful correction, statistical analysis, and repeated verification. It favors long-term consistency over striking individual observations. As confidence grew, so did the implications. Expansion remained the dominant feature of cosmic motion, but it was no longer the whole story. Gravity was sculpting that motion in subtle but measurable ways, creating flows that pointed toward regions of enhanced mass. What once looked like noise turned out to be structure. What once seemed like error became evidence. Motion, stripped of expectation and examined carefully, revealed order rather than chaos. By recognizing peculiar velocity as a collective phenomenon rather than an individual quirk, astronomers gained a new way of reading the universe. Galaxies stopped being just luminous objects scattered through space. They became markers, tracing invisible contours shaped by gravity on the larger scales. Expansion set the background rhythm of the cosmos. Peculiar velocity added texture. Together, They revealed a universe that was not merely growing, but responding, flowing, and subtly shaped by mass far beyond what light alone could show. Long before galaxies formed, before stars ignited or planets cooled, the universe was already glowing. In its earliest moments, everything was hot, dense, and filled with radiation. Matter and light were tightly coupled, constantly colliding, unable to travel freely. As the universe expanded and cooled, a quiet transition took place. At roughly 380,000 years after the beginning, space became transparent. Light was finally able to move without being endlessly scattered. That light never disappeared. It still fills the universe today as a faint, nearly uniform glow known as the cosmic microwave background. It arrives from every direction at almost the same temperature, just a few degrees above absolute zero. Not because it is being produced now, but because it has been travelling ever since the universe first became clear enough to let it go. This radiation was discovered accidentally in the 1960s by Arno Penzias and Robert Wilson. While working with a sensitive radio antenna, they encountered a persistent background signal they could not eliminate. It did not depend on direction. It did not vary with time. No matter where they pointed the instrument, the noise remained. At first it was treated as a nuisance. Equipment was checked. Pigeons were blamed. But eventually it became clear that this signal was not local interference. It was cosmic in origin. What they had found was the cooled remnant of the early universe itself. The cosmic microwave background quickly became one of the most important reference points in cosmology. Because it originated everywhere at once and has been travelling ever since, it provides something remarkably rare, a universal frame of reference. In most of astronomy, motion is always relative. One galaxy moves compared to another. A star shifts against a background of more distant stars. There is no absolute stillness. But the cosmic microwave background offers something close. It represents the universe's earliest large-scale state, before galaxies and clusters introduced local complexity. If an observer were perfectly at rest relative to this radiation, it would appear exactly the same temperature in all directions. No side would look warmer or cooler. Any difference, however small, signals motion. This is where the idea of dipole anisotropy enters. When scientists mapped the cosmic microwave background in detail, they noticed a subtle but systematic pattern. One side of the ski appears slightly warmer, while the opposite side appears slightly cooler. The difference is tiny, measured in thousandths of a degree, but it is consistent and precise. This temperature asymmetry is not random, it arises because of motion. As the Milky Way moves through the background radiation, light coming from the direction of motion is slightly compressed, raising its temperature. Light coming from behind is stretched, lowering its temperature. The effect is similar to the change in pitch of a passing sound, but applied to ancient radiation instead of noise. From this dipole pattern, astronomers can calculate how fast the Milky Way is moving relative to the cosmic microwave background. The result is striking. Our galaxy, along with its local companions, is travelling at roughly 600 kilometers per second relative to this primordial glow. What makes this measurement so powerful is not just the speed, but the reference frame. This motion is not defined relative to nearby galaxies or local structures. It is defined relative to the universe itself, as close as cosmology comes to such a statement. To be clear, this does not mean there is an absolute rest frame in a philosophical sense. The laws of physics still work the same in all inertial frames, but operationally, the cosmic microwave background provides a natural baseline. It allows astronomers to say, with confidence, that the Milky Way is moving in a particular direction through the large-scale universe. Crucially, this velocity cannot be explained by local motion alone. Nearby gravitational influences, such as the interaction between the Milky Way and its neighbouring galaxies, account for only a fraction of the observed speed. The rest must arise from much larger structures exerting their influence over enormous distances. Over the decades, measurements of the cosmic microwave background have improved dramatically. Early maps confirmed its existence and basic uniformity. Later missions refined its structure in exquisite detail. Satellites such as COBE, WMAP, and the Planck mission provided increasingly precise measurements of temperature variations across the entire sky. Each refinement strengthened confidence in the dipole signal. The direction remained the same. The magnitude remained consistent. As uncertainty shrank, the motion became harder to dismiss as error or artifact. What also became clear is that this motion has a direction, not just a speed. The dipole anisotropy points toward a specific region of the sky. The Milky Way is not merely moving relative to the background. It is moving towards something, or more precisely, being influenced from a particular direction. This distinction matters. Random motion would smear out directionality. Local motion would vary from region to region, but the cosmic microwave background dipole provides a clean global indicator. It tells us that the motion is coherent on the largest scales accessible to observation. In effect, the background radiation acts like a cosmic still photograph. Everything moving relative to it leaves a measurable imprint. The universe itself becomes the reference against which motion is judged. There is something quietly humbling about this. The Milky Way, vast as it is, becomes just another moving object in a much larger flow. Its spiral arms, its stars, its planets, all carried along without notice or resistance. Nothing special marks our location. Nothing anchors us in place. At the same time, there is something deeply useful about the cosmic microwave background. It strips away local complexity and provides clarity. By anchoring motion to the universe's earliest light, astronomers can distinguish between what is nearby and what is truly large-scale. This is why the velocity measured relative to the background cannot be dismissed as a local quirk. It reflects the combined gravitational influence of structures far beyond the local group. It points to mass distributions that extend across hundreds of millions of light-years. The background radiation does not tell us what those structures look like. It does not show images or outlines. What it provides is direction. It gives motion context. It reveals that the Milky Way is not drifting aimlessly, nor simply riding along with expansion. Instead, it is responding to gravity on the larger scales we can measure. The cosmic microwave background turns motion into a precise instrument. It allows astronomers to separate expansion from drift, local effect from global influence. It offers a way to measure where the universe itself appears still and how far we are from that state. In doing so, it transforms an abstract idea into something concrete. The universe has a memory. Its earliest light still surrounds us, still measurable, still informative. And against that ancient glow, the ocean of our galaxy becomes unmistakable. We're not simply expanding away from everything else. We are moving through the universe in a specific direction at a measurable speed, relative to the oldest signal we can observe. That fact alone tells us that expansion is only part of the picture, and that gravity, operating quietly across immense distances, is still shaping the flow of galaxies today. Once peculiar velocity was established as something real and meaningful, astronomers began to notice something even more striking. The motion was not confined to individual galaxies or small neighborhoods. It extended outward, linking vast regions of space together. This collective movement became known as bulk flow. Bulk flow describes the shared motion of large groups of galaxies moving together through space, beyond what cosmic expansion alone would predict. Instead of galaxies drifting randomly in different directions, entire regions appear to slide through the universe along a common path. It is not a metaphor. It is a measurable phenomenon, extracted from careful observation and statistical analysis. To understand why this mattered, it helps to imagine what astronomers expected to see. If peculiar velocities were dominated by local effects, then galaxy motion should look increasingly chaotic as larger volumes are considered. Small clusters might show some alignment, but once many clusters were averaged together, their motions should cancel out. Direction would blur. Flow would dissolve into noise. Bulk flow does the opposite. When astronomers examined galaxy velocities across wide swaths of space, they found coherence where randomness was expected. Galaxies separated by tens, then hundreds, of millions of light-years appeared to share a common drift. The motion was subtle, but persistent, and crucially it crossed boundaries that should have disrupted it. Some of the early groundwork for understanding this behavior came from studies by Alan Sandage, whose work on galaxy distances and motions helped refine how peculiar velocities were measured. Sandage was deeply interested in separating cosmic expansion from other influences, and his careful approach to distance indicators made it possible to look for patterns that would otherwise be lost in uncertainty. At the same time, focused observational efforts such as the Virgo cluster surveys played a key role. The Virgo cluster is one of the nearest large galaxy clusters, making it an ideal laboratory for studying motion in detail. By measuring how galaxies in and around Virgo moved relative to one another, astronomers could test whether motion was confined to the cluster itself or part of something larger. What emerged was surprising. The motion of galaxies associated with Virgo did not stop at the cluster's edge. It blended smoothly into the motion of surrounding galaxies. The flow did not respect neat boundaries. It behaved as if clusters were embedded within a larger current rather than acting as isolated systems. This observation pushed astronomers to think differently about scale. Galaxies belong to clusters, clusters belong to superclusters, and superclusters belong to even larger arrangements of matter. Motion, it seemed, followed this hierarchy. The larger the scale considered, the smoother and more coherent the motion became. Bulk flow is identified statistically, not visually. Astronomers collect velocity measurements across large regions and calculate the average motion within that volume. If the average differs significantly from zero and does so consistently across independent data sets, it indicates a real flow rather than random fluctuation. The key word here is consistency. Random motion fluctuates. It changes direction as more data are added. Its signal weakens when samples grow. Bulk flow behaves differently. As surveys expanded and more galaxies were included, the signal persisted. In some cases it became clearer. To assess this rigorously, astronomers rely on statistical confidence thresholds. These thresholds help determine whether an observed pattern is likely to be real or simply the result of chance. When bulk flow measurements repeatedly exceeded these thresholds, confidence grew that the effect was physical. This was not based on a single survey or method. Different teams using different techniques arrived at compatible results. Optical surveys, infrared observations and distance indicators based on entirely different physics, All pointed in the same general direction. Agreement across surveys mattered enormously. It reduced the likelihood that bulk flow was an artifact of a particular instrument or assumption. One of the more intriguing aspects of bulk flow is that it appears to extend across cluster boundaries. Individual clusters are gravitationally bound systems, dominated by their own internal dynamics. Yet bulk flow does not stop when a cluster ends. It carries clusters along as part of a larger motion. This behavior reveals something fundamental about gravity on large scales. Gravity does not operate in isolation. Massive structures influence not only their immediate surroundings, but also regions far beyond their visible edges. When enough mass is distributed unevenly across space, its combined gravitational pull can organize motion across enormous distances. Bulk flow also highlights an important contrast with random motion. In random systems, direction varies widely and unpredictably. In bulk flow, direction is shared. The galaxies involved are not coordinating, of course. They are responding independently to the same gravitational landscape. The coordination emerges naturally from the structure itself. There is a gentle irony here. The universe often appears chaotic up close. Individual galaxies collide, stars explode, and matter swirls unpredictably. Yet when viewed from far enough away, patterns emerge that are smoother and more orderly than intuition might suggest. Bulk flow is one of those patterns. From a practical standpoint, bulk flow became a powerful diagnostic tool. By measuring how fast and in what direction large regions of space move, astronomers could infer the distribution of mass beyond what could be seen directly. Motion became a tracer. It revealed the presence of large-scale structures even when those structures were partially hidden or difficult to observe. This marked a transition in cosmology. The focus shifted from individual galaxies to structure itself. Galaxies became markers embedded in a cosmic framework defined by gravity and mass distribution. Their motion told a story about the shape of that framework. There was also an important methodological lesson. Bulk flow could not be established with small data sets. It required patience, scale, and repeated verification. Only by combining observations across large volumes could the signal emerge clearly. This reinforced the value of large surveys and collaborative science. Gentle humor occasionally surfaced in discussions of bulk flow, often framed around the idea that galaxies were behaving more politely than expected. Instead of scattering chaotically, they seemed to agree on a direction, as if following an unspoken rule. Of course, the rule was gravity, quietly doing what gravity does. As confidence in bulk flow grew, so did its implications. If galaxies and clusters were moving together across vast regions, then the source of that motion must itself be vast. Local explanations no longer sufficed. The cause had to lie in the large-scale structure of the universe, in mass concentrations spread across hundreds of millions of light-years. This realization nudged cosmology toward a broader view. Motion was no longer just a property of objects, it was a property of regions. It reflected how matter was arranged on the largest scales accessible to observation. By the time bulk flow was firmly accepted, it had become clear that understanding galaxy motion required understanding structure. Expansion provided the background rhythm. Peculiar velocity added texture. Bulk flow revealed the underlying currents. Galaxies, clusters, and superclusters were not isolated features sprinkled randomly through space. They were connected parts of a larger pattern, moving together in response to gravitational influences that transcended individual systems. In this way, bulk flow served as a bridge. It linked the behavior of galaxies to the architecture of the universe itself. Motion stopped being a local curiosity and became a map, guiding astronomers toward the unseen structure shaping the cosmic landscape. When astronomers first tried to explain the motion of the Milky Way, they began close to home. The most immediate gravitational environment is the local group, a modest collection of galaxies bound together by gravity. It contains a few dozen members, most of them small dwarf galaxies, spread across a region a few million light-years wide. At its centre sit two dominant spirals, the Milky Way and the Andromeda Galaxy. On paper, this looks like a reasonable place to search for answers. Gravity acts most strongly at close range, and nearby objects should exert the greatest influence. If the Milky Way is drifting through space, then surely the explanation must begin with its closest neighbours. The mass of the local group is substantial, but not enormous by cosmic standards. Estimates place its total mass at a few trillion times the mass of the Sun, most of it not in stars but in extended halos of unseen matter surrounding each galaxy. This mass is enough to keep the group gravitationally bound and to shape the orbits of its members over billions of years. The most influential partner in this system is Andromeda. Slightly larger than the Milky Way and approaching at a speed of over 100 kilometers per second, it dominates the local gravitational conversation. The two galaxies are locked in a slow dance that will eventually bring them together far in the future. Because this interaction is so prominent, early attempts to model galactic motion often treated the Milky Way and Andromeda as a two-body system. In classical mechanics, two-body dynamics are wonderfully predictable. Given the masses, positions, and velocities, the future motion can be calculated with impressive accuracy. This approach works beautifully for planets and stars, it works reasonably well for binary galaxies, and it works just well enough for the local group to be tempting. But when astronomers applied these models to the Milky Way's observed motion, something did not line up. Two-body dynamics predict motion along a specific axis, largely defined by the line connecting the Milky Way and Andromeda. They predict speeds that depend directly on the masses involved. When these predictions were compared to the velocity measured relative to the broader universe, the numbers fell short. The Milky Way was moving too fast and not quite in the right direction. Even when the full mass of the local group was included, including generous estimates for unseen matter, the gravitational pull simply was not strong enough. The predicted motion accounted for only a portion of what was observed. Something else was contributing, something beyond the immediate neighbourhood. This mismatch was not subtle. As models improved and measurements became more precise, the gap remained. The local group explained local interactions well, but it could not explain large-scale drift. Researchers at institutions such as the Harvard-Smithsonian Center for Astrophysics explored this problem in detail, building increasingly sophisticated dynamical models. These models included not just the Milky Way and Andromeda, but also the collective influence of the group's smaller members and their extended dark matter halos. The result was consistent. Local gravity mattered, but it was not dominant. This led astronomers to re-examine one of the most useful tools in modern astrophysics, the mass-to-light ratio. This ratio compares how much mass an object has to how much light it emits. Stars shine, gas glows, mass pulls. When the pull exceeds what the light can explain, something unseen must be present. In galaxies and clusters, mass-to-light ratios are often far higher than what visible matter alone would suggest. This is one of the strongest lines of evidence for dark matter. By estimating these ratios, astronomers can infer how much total mass is present, even when most of it does not shine. Applying this approach to the local group reinforced the problem. Even when dark matter was included generously, The total mass still could not account for the Milky Way's motion relative to the cosmic microwave background. The numbers refused to cooperate. Visible matter failed first. Invisible matter followed soon after. This failure was not frustrating. It was informative. It told astronomers that the cause of the Milky Way's motion could not be local. It couldn't be explained by nearby galaxies, no matter how carefully their masses were estimated. The influence shaping this motion had to extend far beyond the local group, reaching into regions of space that dwarfed our immediate surroundings. There is an important conceptual shift here. Gravity does not stop at the edge of a group or cluster. It accumulates. Many small pulls, spread across enormous distances, can combine into a significant influence. The universe does not care about tidy boundaries drawn on maps. This is where intuition often fails. Human experience teaches that distant objects matter less. In everyday life, a faraway mountain has little influence compared to a nearby wall. In cosmology, distance matters differently. When mass is distributed across vast volumes, its collective pull can shape motion on scales that feel counterintuitive. The local group is not isolated. It sits within a larger arrangement of galaxies, which itself is part of an even larger structure. Each layer adds its contribution. Individually, these contributions are small. Together, they become decisive. This realization marked a turning point. Instead of refining local models endlessly, astronomers accepted that the explanation lay elsewhere. The question shifted from what nearby objects were doing to how mass was arranged across much larger regions of the universe. There was also a methodological lesson embedded in this failure. Models are only as good as their assumptions. Two-body dynamics assume isolation. The universe does not offer that luxury. Every system is embedded within a larger one, influenced by forces that extend well beyond its apparent edges. The Milky Way's motion made this impossible to ignore. Its speed and direction carried information about mass far beyond what could be seen directly. Local gravity explained the details. Distant gravity explained the trend. At this point, the focus naturally moved outward, away from individual galaxies, away from small groups, toward clusters, superclusters, and the large-scale distribution of matter itself. The failure of local gravity was not a dead end. It was a signpost. It told astronomers where not to look, and in doing so pointed them toward where the real influence must lie. The Milky Way was responding to something much larger than its immediate neighborhood. Its motion was a response to structure on scales that demanded a broader view. Local gravity sets the stage. It governs orbits, mergers, and close interactions. But when it comes to the long, slow drift of galaxies through the universe, it does not have the final word. To understand that drift, one has to stop thinking locally and start thinking cosmically. Once local gravity was ruled out as the main driver of large-scale motion, astronomers were forced to widen their view dramatically. The universe could no longer be treated as a collection of isolated islands of matter. Instead, it had to be understood as a connected system, shaped by gravity acting over immense distances. Out of this shift came what is now known as cosmic web theory. At the larger scales, matter in the universe is not spread evenly. It arranges itself into a vast interconnected network made up of long filaments, dense nodes, and enormous empty regions called voids. Galaxies are not scattered randomly through space like grains of sand. They trace these structures, clustering along invisible scaffolding that stretches across hundreds of millions of light years. Filaments are the highways of this network. They are elongated regions where matter has collapsed into long strands under gravity. Along these filaments, galaxies are more numerous and more tightly packed. Nodes sit at the intersections of filaments, where matter has flowed together from multiple directions. These nodes often host massive galaxy clusters. Between filaments and nodes lie voids, immense regions with very little matter at all where galaxies are rare and motion is comparatively gentle. This picture did not emerge from observation alone. It was predicted, tested, and refined through decades of computational work. One of the most influential efforts in this area was the Millennium Simulation Project, which used powerful computers to model how matter evolves under gravity over cosmic time. Starting with conditions inferred from the early universe, the simulation allowed gravity to do its work step by step over billions of simulated years. The result was striking. Without imposing any preferred shapes or patterns, the simulation naturally produced a web-like structure that closely resembled what astronomers observe today. Filaments formed, nodes emerged, voids opened up, galaxies flowed along predictable paths dictated by the underlying distribution of mass. This success reinforced a key idea. Structure formation in the universe is driven by gravity, acting on tiny initial differences in density. In the early universe, matter was distributed almost evenly, but not perfectly. Slight overdensities exerted slightly stronger gravitational pull. Over time, those regions attracted more matter, becoming denser still. Underdense regions lost matter and expanded into voids. Crucially, this collapse does not happen uniformly in all directions. This is known as anisotropic collapse. Matter falls inward fastest along the shortest dimensions first. Instead of collapsing straight into compact spheres, matter stretches into sheets and filaments before finally pooling into dense nodes. Gravity sculpts structure step by step, guided by geometry as much as by mass. This process underpins large-scale structure formation. It explains why the universe looks stringy rather than clumpy when viewed at the larger scales. It also explains why motion is not random. Galaxies do not simply wander through space. They move along pathways defined by the gravitational landscape. Once a filament begins to form, it acts like a channel. Matter within its reach tends to flow along it, guided toward denser regions. Galaxies embedded in these filaments inherit this motion. They drift not because they are being pulled toward a single nearby object, but because they are responding to the collective pull of mass distributed along the structure. This is where motion and structure become inseparable. The paths galaxies take are written into the shape of the cosmic web itself. To understand why galaxies move the way they do, one must understand the geometry of the structures they inhabit. There is a subtle elegance here. The universe does not need coordination. No signal tells galaxies where to go. Each responds locally to gravity, yet the outcome is large-scale order. Emergent order arises naturally from simple rules applied repeatedly across vast scales. This is one of the most counterintuitive aspects of cosmology. Chaos dominates small systems. On Earth, weather is unpredictable beyond a few days. Human crowds behave erratically. Yet on the largest scales imaginable, the universe settles into patterns that are remarkably stable and reproducible. Motion becomes a consequence of structure rather than an independent phenomenon. Galaxies move because the web exists. The web exists because gravity amplifies small differences over time. Neither can be fully understood without the other. Observations have repeatedly confirmed this picture. Large redshift surveys show galaxies tracing filaments exactly where simulations predict them to be. Voids appear where models say they should. Clusters sit at nodes, fed by multiple filaments like rivers meeting at a delta. What is especially important for understanding large-scale motion is that these structures extend far beyond the reach of individual galaxy clusters. A filament can span hundreds of millions of light-years, linking distant regions into a single dynamical system. Motion along such a structure does not respect the boundaries of clusters or groups. It flows through them. This explains why bulk motion crosses cluster boundaries so easily. A cluster is not a closed system in the cosmological sense. It is a dense knot in a much larger web. Galaxies fall into clusters along filaments, carrying with them the momentum acquired over vast distances. The cluster absorbs that motion, but it does not erase it. From this perspective, the motion of the Milky Way is no longer puzzling. It is not being tugged randomly, nor is it responding only to nearby neighbours. It is embedded in a structured universe, moving along gradients established by the distribution of mass on scales far larger than the local group. The cosmic web also explains why direction matters so much. In a uniform universe, direction would be meaningless. Motion would average out. In a structured universe, direction encodes information about where mass lies. Following the motion of galaxies is like following the slope of a landscape. You may not see the entire terrain, but the direction of flow tells you where the low points are. This insight sets the stage for inference-based discovery. Astronomers do not need to see every mass concentration directly. By measuring how galaxies move, they can reconstruct the shape of the underlying web. Motion becomes a proxy for structure. Velocity becomes a map. There is a quiet shift in perspective that happens here. The universe stops being thought of as a collection of objects and starts being understood as a system. Individual galaxies matter less than the patterns they participate in. What counts is not where a galaxy is, but how it moves relative to others. Even the emptiest regions play a role. Voids are not merely gaps. They expand and push matter outward toward filaments, enhancing flow along the web. Their presence helps shape motion just as much as dense clusters do. Absence influences behavior as surely as presence. This is one reason why large-scale motion cannot be explained by a single nearby source. The forces involved are distributed, cumulative, and structural. They arise from the shape of the universe itself, not from any one object acting alone. The cosmic web offers a framework that ties everything together. Expansion provides the background stretching of space. Gravity shapes that space into filaments and nodes. Motion traces those shapes over time. Each element reinforces the others. By the time this framework was widely accepted, it had transformed how cosmologists interpreted motion. Drift was no longer a mystery to be solved in isolation. It was a natural outcome of living in a structured universe. And once structure is taken seriously, motion stops being surprising. It becomes expected. Much of what shapes the universe cannot be seen directly. This is not a philosophical statement. It is a practical one. Astronomy began as a science of light. Stars were catalogued because they shone. Galaxies were discovered because they glowed faintly against the dark. For a long time, it was natural to assume that what mattered most was what could be observed visually. But as measurements improved and expectations sharpened, it became clear that light tells only part of the story. This is where gravitational inference enters the picture. Gravitational inference is the practice of determining the presence, distribution, and influence of mass by observing its effects rather than its appearance. Instead of asking what is visible, astronomers ask what must exist in order to produce the motions they measure. In this approach, movement becomes evidence, acceleration becomes testimony, drift becomes data. The principle is straightforward. Mass curves space and influences motion. If an object changes speed or direction, something has acted on it. When large numbers of objects show coordinated motion, the cause must be correspondingly large. Gravity does not leave fingerprints in light alone, it leaves them in trajectories. This way of thinking has deep roots. Long before modern cosmology, unseen mass was inferred from motion. Neptune was discovered because Uranus did not move as expected. The unseen planet revealed itself through gravitational influence long before it was seen through a telescope. The same logic applies on vastly larger scales. In cosmology, however, the challenge is scale and complexity. Galaxies are not test particles moving through empty space. They sit within an expanding universe, embedded in a web of matter that stretches across immense distances. Extracting gravitational information from their motion requires careful modelling and restraint. One of the key figures in developing this framework was the Soviet physicist Yakov Zeldovich. Zeldovich approached the problem of structure formation by asking how small initial differences in density could evolve under gravity into the complex structures observed today. His work bridged theory and observation in a way that proved remarkably powerful. From this effort emerged what is now known as the Zeldovich approximation. Despite the name, it is not a rough guess. It is a mathematically grounded method for describing how matter flows under gravity in the early stages of structure formation. It provides a way to predict how regions of slightly higher density collapse first along one direction, then another, shaping filaments and sheets before forming dense nodes. The importance of the Zeldovich approximation lies not in its precision at late times, but in its insight. It shows that motion and structure are inseparable. Matter does not simply clump randomly. It follows predictable paths shaped by gravity and geometry. These paths can be inferred from how objects move today. Building on this idea, astronomers develop techniques for reconstructing velocity fields. A velocity field is a map that shows how fast and in what direction matter is moving at different locations in space. Unlike a photograph, it does not show what things look like. It shows how they behave. To create such a field, astronomers collect velocity measurements from many galaxies across a wide region. Each measurement carries uncertainty. Each galaxy has its own local motion layered on top of the large-scale flow. To reveal the underlying pattern, these data must be combined carefully. This is where statistical smoothing comes in. Statistical smoothing is not about hiding information. It is about extracting signal from noise. By averaging motion over carefully chosen volumes, local irregularities fade while large-scale trends remain. Small-scale chaos gives way to broad coherence. The result is not a perfect map, but a reliable representation of the dominant flows. Smoothing must be applied thoughtfully. Too little smoothing leaves the data noisy and misleading. Too much smoothing erases genuine structure. The art lies in choosing scales that reflect the physics involved. Gravity operates differently at different distances, and the analysis must respect that. These reconstructions rely on assumptions, and astronomers are explicit about them. They assume that gravity dominates motion on large scales. They assume that galaxies trace the underlying mass distribution reasonably well. They assume that expansion has been correctly accounted for. None of these assumptions are taken lightly, and all are tested against observations. Uncertainty is an unavoidable part of inference. Distance measurements are imperfect. Velocities have error bars. Sampling is incomplete. But uncertainty does not invalidate inference. It defines its limits. When independent methods converge on the same result despite different assumptions and data sources, confidence grows. This is why gravitational inference has earned trust. It is not based on a single clever trick. It is supported by consistency across approaches. When simulations, velocity reconstructions, and large-scale surveys all point to the same structures, the invisible becomes hard to dismiss. There is a tendency to treat direct imaging as the gold standard. If something can be seen, it feels real. If it must be inferred, it can feel speculative. In practice, the opposite is often true. Direct images can mislead when important components do not emit light. Inference, grounded in physics, can be more complete. Consider dark matter. It does not shine. It does not absorb light in any obvious way. Yet its gravitational influence is unmistakable. Rotation curves of galaxies, motions within clusters, and large-scale flows all demand its presence. Dark matter is one of the best examples of how indirect evidence can be overwhelming. Gravitational inference operates on the same principle. It does not guess what exists. It calculates what must exist for the universe to behave as observed. This distinction matters. There is also a philosophical comfort in this approach. It acknowledges limits without surrendering understanding. Astronomers do not need to see everything to know something. They can accept that some regions are obscured, distant, or inaccessible, while still extracting meaningful information. This becomes especially important when dealing with regions hidden from view. Dust, gas, and intervening structures can block light across entire swathes of the sky. Some of the most influential mass concentrations lie precisely where visibility is poorest. In these cases, inference is not optional. It is the only tool available. Motion does not care whether mass is visible. Gravity acts regardless of illumination. Galaxies respond to the total mass around them, not just the part that shines. By following their motion, astronomers can trace influences that telescopes alone cannot reveal. There is a quiet robustness to this method. It does not depend on a single wavelength or instrument. It works across optical, infrared, and radio surveys. It is supported by theory, simulation, and observation. Its conclusions sharpen as data improve rather than unravel. That reliability is why inference-based techniques have become central to modern cosmology. They allow scientists to move beyond the limitations of direct observation and engage with the universe as it actually behaves, not just as it appears. As maps of velocity fields improved and reconstructions grew more detailed, patterns began to emerge with increasing clarity. Flows aligned, directions converged. The invisible began to take shape through its effects. What was once hidden by darkness and distance became legible through motion. The universe, it turned out, was willing to reveal itself, provided one learned how to listen to how it moves. And in regions where light fails entirely, motion continues to speak. There is a region of the sky that astronomers learned very early on to distrust. Not because it was empty, but because it refused to cooperate. This region runs like a broad band across the sky, aligned with the plane of the Milky Way itself. When astronomers pointed optical telescopes into it, distant galaxies seemed to vanish. Surveys that worked beautifully elsewhere suddenly thinned out. Catalogues became sparse, patterns dissolved. This came to be known as the zone of avoidance. The name is practical rather than dramatic. It reflects a simple reality. When looking outward through the dense disk of our own galaxy, astronomers are forced to peer through thick clouds of dust and gas. These materials absorb and scatter visible light extremely efficiently. Distant galaxies may still be there in vast numbers, but their light never reaches us in usable form. The Milky Way from the inside is not a transparent place. Its disk is packed with cold molecular clouds, diffuse dust grains, and glowing gas regions that are wonderful for studying star formation nearby, but deeply inconvenient when trying to see beyond. Optical light coming from distant galaxies is dimmed, reddened, and often completely erased before it can escape the galactic plane. Early sky surveys relied almost entirely on visible light. This worked well away from the plane of the Milky Way, where the sky opened up and galaxies appeared in abundance. But as surveys expanded and maps filled in, a conspicuous gap remained. A broad, uneven strip where the universe seemed to thin out unnaturally. At first, this absence was tempting to interpret literally. Perhaps there really were fewer galaxies there. Perhaps the universe was structured in some peculiar way. But the alignment was too perfect. The empty region traced the Milky Way exactly. The explanation was local, not cosmic. Optical surveys had failed, not because the universe was empty, but because our vantage point was obstructed. This created a serious problem. Motion measurements, bulk flows, and velocity reconstructions were increasingly pointing toward a direction that lay suspiciously close to this obscured region. The direction of shared galactic motion appeared to line up with the zone of avoidance itself. This coincidence was unsettling. On the one hand, motion data suggested that something massive lay in that direction. On the other hand, direct observation showed almost nothing at all. The very region that seemed most important dynamically was the one that could not be seen clearly. Astronomers were forced to confront a bias that has been quietly shaping their understanding. Surveys are only as good as what they can detect. If a large portion of the sky is effectively invisible to the primary tools being used, then any conclusions drawn from those surveys are incomplete by definition. This was not a minor blind spot. The zone of avoidance covers a significant fraction of the sky. Entire clusters of galaxies could hide there unnoticed. Large-scale structures could pass undetected simply because they lay behind the dust and gas of our own galaxy. Early maps of the universe reflect this clearly. When plotted in galactic coordinates, they show a dense distribution of galaxies everywhere except along the galactic plane, where a conspicuous gap slices across the data. The universe, on paper, looked torn in half. This was deeply frustrating for astronomers. Theoretical models and velocity measurements demanded mass in that region. Observations stubbornly refused to reveal it. The tools that had served so well elsewhere were suddenly inadequate. Efforts to map the region intensified. Observatories such as the European Southern Observatory undertook targeted campaigns to probe as deeply as possible into the obscured sky. Even so, optical observations could only go so far. The dust was not thin or patchy. It was thick, structured, and relentless. The frustration was not just technical, it was conceptual. Cosmology relies on completeness. Patterns only make sense when seen in full. Missing regions distort averages, bias reconstructions, and complicate inference. The zone of avoidance was not just hiding galaxies, it was hiding certainty. Yet the coincidence with motion could not be ignored. The bulk flow of galaxies, the dipole seen in the cosmic microwave background, and velocity field reconstructions all pointed in roughly the same direction, and that direction ran straight into the observational wall created by the Milky Way. This raised an uncomfortable possibility. What if some of the most influential structures in the nearby universe lay precisely where our view was worst? In hindsight, this is almost obvious. The Milky Way does not choose its orientation based on cosmological convenience. It simply happens to sit where it sits. If large-scale structure exists behind it, That is unfortunate but irrelevant to gravity. Gravity does not care whether mass is visible. From a methodological standpoint, this forced a reassessment. Astronomers could no longer rely on optical surveys alone to build a complete picture of nearby structure. The universe was not obligated to reveal itself in the wavelengths most convenient to human eyes. The zone of avoidance became a test case for scientific humility. It highlighted how easily observational bias can masquerade as cosmic truth. Where data are missing, imagination rushes in unless caution intervenes. There was also a subtle psychological effect. Maps that look complete inspire confidence. Gaps undermine it. The presence of a persistent blind region meant that even the best sky maps came with an asterisk. They were impressive, but not finished. This did not stall progress. Instead, it redirected it. If visible light could not penetrate the galactic plane, then other wavelengths would have to be used. Infrared light, radio waves, and other parts of the electromagnetic spectrum interact with dust and gas differently. Some pass through with relatively little interference, others reveal entirely different aspects of the universe. The realization was simple and powerful. The zone of avoidance was not truly empty. It was merely optically inconvenient. Before those alternative approaches could fully take hold, astronomers had to accept a difficult truth. Some of the strongest gravitational influences shaping the motion of nearby galaxies were hidden from direct view. The evidence for their existence came not from images, but from motion itself. This reinforced the importance of inference-based techniques. When light fails, gravity still speaks. The zone of avoidance became a region where indirect evidence mattered more than direct observation, where motion had to substitute for sight. It also reframed frustration as opportunity. If mass could hide so effectively in one region, then uncovering it would not only resolve local mysteries, but also test the robustness of cosmological methods. Success there would validate inference everywhere else. The zone of avoidance, once seen as an obstacle, became a proving ground, a place where the universe reminded astronomers that seeing is optional, but measurement is not. And so attention shifted, not away from the obscured region, but deeper into it, armed with new tools, new wavelengths, and a growing confidence that even the darkest parts of the sky could be understood, provided one stopped insisting on looking at them in only one way. Once it became clear that visible light could not provide a complete map of the nearby universe, astronomers began looking for ways to see through the Milky Way rather than around it. The obstruction was not mysterious. Dust grains and cold gas block optical light efficiently, but they do not affect all wavelengths equally. If one part of the spectrum was failing, others might succeed. This realization marked the beginning of a quiet shift in observational strategy. Infrared astronomy was one of the first breakthroughs. Infrared light has longer wavelengths than visible light, allowing it to pass through dust with far less scattering and absorption. Regions that appeared opaque in optical images suddenly became translucent. The Milky Way's dense plane no longer looked like a wall, but like a fog. One of the earliest large-scale efforts to exploit this was the Infrared Astronomical Satellite, often known as IRAS. Launched in the 1980s, it surveyed the entire sky in infrared wavelengths, producing a map unlike anything that had come before. Structures hidden in optical surveys began to emerge faintly but unmistakably. IRAS did not reveal everything. Its resolution was limited, and its sensitivity was modest by modern standards. But it proved something crucial. The zone of avoidance was not empty. Galaxies were there, and in significant numbers. Their infrared glow, often dominated by warm dust heated by stars, leaked through the Milky Way's obscuring veil. This success encouraged more ambitious surveys. The 2-micron all-sky survey, known as 2MASS, expanded this approach dramatically. Operating in near-infrared wavelengths, it mapped the entire sky with far greater resolution and sensitivity than earlier efforts. Where optical catalogues showed gaps, 2MASS revealed continuity. Filaments extended across the galactic plane. Clusters appeared where none had been visible before. The effect was not subtle. Entire structures that seemed to stop abruptly at the edge of the Milky Way were suddenly seen to continue straight through it. The universe, once sliced by an artificial blind spot, began to look whole again. Infrared observations, however, are only part of the solution. While dust becomes less of an obstacle, distance measurements remain challenging. Infrared light can reveal the presence of galaxies, but determining how far away they are requires additional information. Brightness alone is not enough, especially when dust still dims and reddens signals unevenly. This is where radio astronomy became essential. Radio waves pass through dust and gas almost unimpeded. They offer a way to probe the universe that is nearly immune to the Milky Way's obscuring effects. One of the most important radio signatures for mapping galaxies is the emission from neutral hydrogen. This emission provides both detection and velocity information, making it invaluable for studying large-scale motion. Facilities such as the Parkes radio telescope played a central role in this effort. By surveying the sky in radio wavelengths, Parkes and similar instruments detected galaxies completely invisible in optical surveys. Neutral hydrogen emissions revealed not just isolated galaxies, but extended structures hidden behind the galactic plane. These radio surveys filled in crucial gaps. They confirmed that massive structures existed precisely where motion measurements suggested they should. The alignment between inferred motion and newly revealed mass was not perfect, but it was compelling. For the first time, astronomers could begin to connect the dots across the zone of avoidance. Yet even with these advances, limitations remained. Infrared and radio observations come with their own challenges. Infrared surveys can struggle with confusion in dense regions, where many sources overlap. Radio surveys often have lower angular resolution, making it difficult to separate closely packed galaxies. Distance uncertainty remained one of the most stubborn problems. Knowing that a galaxy exists is not the same as knowing where it sits in three-dimensional space. Redshift provides velocity information, but converting that into distance is complicated by peculiar velocity itself. Ironically, the very motion astronomers were trying to explain made distance estimates harder. This created a layered problem. Motion was needed to infer mass, but mass was needed to interpret motion. Astronomers navigated this by combining multiple methods, cross-checking results, and accepting uncertainty where it could not yet be reduced. What mattered most was not perfection, but improvement. Each new survey peeled back another layer of obscuration. Structures that were once entirely hidden became partially visible. Velocity reconstructions grew more constrained. The universe behind the Milky Way stopped being a complete mystery and became an incomplete but increasingly legible region. There is a temptation to think of scientific progress as a series of clean solutions. In reality, it is often a process of gradual clarification. Infrared and radio astronomy did not eliminate the zone of avoidance. They softened it. They turned an absolute blind spot into a region of limited visibility. This distinction matters. Even today, no survey sees everything equally well. Some regions remain difficult. Some structures are still only partially mapped. The universe does not yield all its information at once, and it does not promise completeness on demand. What changed was confidence. Astronomers could now say, with evidence rather than inference alone, that the hidden regions contained substantial mass. The coincidence between motion direction and obscured structure was no longer speculative. It was supported by data arriving from multiple wavelengths and independent instruments. There was also a shift in mindset. Instead of treating the Milky Way as an obstacle, astronomers began treating it as a filter. Each wavelength revealed a different aspect of what lay beyond. No single view was sufficient, but together they formed a composite picture richer than any individual survey could provide. This multi-wavelength approach became standard practice. Optical surveys mapped what they could. Infrared surveys filled in dusty regions. Radio observations traced gas and motion. Each compensated for the weaknesses of the others. The result was not a perfect map, but a far better one than had ever existed before. It also reinforced a deeper lesson. Visibility is not the same as importance. Some of the most influential structures shaping the motion of galaxies are not the brightest or most photogenic. They are massive, extended, and sometimes inconveniently placed behind our own galaxy. The Milky Way, once thought of as window onto the universe, turned out to be a veil as well. Learning to see through it required patience, creativity, and a willingness to abandon the idea that one tool or one wavelength could reveal everything. Even now, astronomers speak carefully about what is known and what remains uncertain. The region behind the galactic plane is better understood than ever, but it is not fully transparent. Some structures remain only partially resolved. Some distances remain approximate. This incomplete visibility is not a failure. It is a reminder of scale. The universe is vast, complex, and indifferent to our preferred vantage points. Progress comes not from eliminating uncertainty entirely, but from reducing it steadily, layer by layer. By learning to see through the Milky Way rather than around it, astronomers transformed a major obstacle into a manageable challenge. The zone of avoidance shrank not in size, but in significance. What once blocked understanding became another region where motion, inference, and multi-wavelength observation worked together. The universe did not become fully visible, but it became visible enough. Once astronomers accepted that motion itself carried information, the natural next step was to stop treating velocity as a side measurement and start treating it as the primary signal. Instead of asking where galaxies are, they began asking how galaxies move and whether those motions could be assembled into something coherent. This shift marked the rise of velocity field mapping, an approach that treats the universe less like a photograph and more like a flowing landscape. A velocity field is, at its core, a map of motion. At each point in space it describes the direction and speed at which matter is moving. Unlike images, which capture light emitted at a particular moment, velocity fields capture behavior. They reveal trends that are invisible in static snapshots. Constructing such a map is not straightforward. Individual galaxy velocities are noisy. Each galaxy carries its own local peculiar motion layered on top of larger flows. Distance estimates introduce uncertainty. Observational gaps distort coverage. Left untreated, the data resemble static more than signal. The breakthrough came from recognizing that gravity imposes order on motion, even when individual measurements appear messy. If gravity dominates large-scale dynamics, then velocity fields should be smooth, continuous, and describable with relatively simple mathematical structure. One of the most influential tools developed to extract this structure was the potent method. The name reflects its core idea. reconstructing the gravitational potential underlying observed motions. Rather than focusing on individual velocities, the method treats the velocity field as the gradient of a gravitational potential. In simple terms, it assumes that matter flows downhill in a gravitational landscape. This approach was advanced significantly by Avishai Deckel and collaborators who recognized that peculiar velocities could be inverted to reveal the distribution of mass that produced them. Instead of guessing where mass might be, they let the motion speak for itself. The logic is elegant. If gravity is the dominant force shaping motion on large scales, then velocity should be coherent and curl-free. That means they can be described as flowing toward regions of greater mass concentration. By mathematically reversing this flow, one can reconstruct where those concentrations must lie. This process leads naturally to the idea of gravitational basins. A gravitational basin is a region of space toward which surrounding matter flows. It is not necessarily a single object. It can be an extended region, where mass density is higher than average. Galaxies within the basin drift inward over time, not because they are being pulled toward a point, but because they are responding to a broad gravitational gradient. Velocity field reconstruction makes these basins visible, not as luminous structures, but as converging motion patterns. Flow lines trace the paths matter follows, much like streamlines in fluid dynamics. Where many flow lines converge, a basin is indicated. These flow lines are powerful because they do not rely on seeing the mass directly. They rely on consistency. If galaxies across a wide area all drift in directions that point toward the same region, that region must exert a significant gravitational influence. Importantly, these reconstructions are statistical rather than deterministic. No single galaxy defines a basin. It emerges only when many measurements are combined. This is where smoothing and averaging return, not as blunt tools but as precision instruments. To assess reliability, astronomers define statistical confidence regions. These regions describe where a reconstructed basin is most likely to lie, given the uncertainties in the data. Instead of claiming exact locations, scientists describe volumes where the influence is concentrated with high probability. What made this approach convincing was repeatability. Different data sets, collected using different methods and wavelengths, produce similar velocity fields. Optical surveys, infrared observations, and radio measurements all contributed velocity information. When processed independently, they pointed toward the same general flow patterns. This convergence mattered more than any single result. If velocity field reconstructions depended heavily on a particular survey or assumption, they would be fragile. Instead, they proved remarkably robust. Changing the input data altered details, but not the overall structure. Obscuration remained an issue, particularly near the plane of the Milky Way. But the velocity field did not collapse in these regions. Because flow is continuous, missing data could often be interpolated without inventing structure. Motion upstream and downstream constrained what must be happening in between. This is one of the strengths of inference-based mapping. Gaps do not automatically destroy coherence. As long as enough surrounding data exist, the overall pattern remains legible. Obscuration complicates analysis, but it does not invalidate it. There is a quiet discipline to this kind of work. It avoids dramatic claims. It resists overinterpretation. It accepts uncertainty openly while still extracting meaningful structure. Velocity field mapping does not promise exact answers. It promises consistent ones. As reconstructions improved, a striking picture emerged. Large regions of space appeared to flow coherently toward a particular area. The flow was not sharp or funnel-like. It was broad, gentle and persistent. Galaxies did not rush inward, they drifted. This behavior is difficult to produce accidentally. Random motion does not align over such distances. Local interactions cannot coordinate flow across hundreds of millions of light years. Only a large-scale gravitational influence can produce such coherence. Another important feature of these reconstructions was scale separation. On small scales, velocity fields remained complex and noisy. On large scales, they smoothed into simple patterns. This matched theoretical expectations. Gravity averages behavior over distance, filtering out small-scale chaos. The reconstructed basins were not hypothetical constructs layered on top of the data. They were demanded by the data. Remove the basin, and the motion no longer made sense. The flow lines lost direction. Coherence vanished. This made the next step almost inevitable. Once a gravitational basin is identified consistently across methods and datasets, it becomes something that can be named, discussed, and tested further. Naming is not discovery, but it marks recognition. It signals that an inferred structure has crossed a threshold of confidence. Before that could happen, astronomers needed to be certain that the signal was not an artifact of methodology. Extensive testing followed. Alternative assumptions were explored. Different smoothing scales were applied. The results remained stable. There was also a conceptual shift underway. Motion was no longer seen as something galaxies happened to have. It was seen as something imposed by structure. Galaxies traced flows because flows defined the gravitational landscape they inhabited. This perspective inverted the traditional view. Instead of mapping matter first and explaining motion afterward, astronomers were now mapping motion to explain matter. The universe revealed its structure through behavior rather than appearance. There is something quietly satisfying about this reversal. It treats gravity with the respect it deserves. Gravity does not need to be seen to be felt. It announces itself through influence, not spectacle. By the time velocity field mapping matured, the evidence was no longer subtle. The Milky Way was not moving independently. It was part of a larger flow responding to a gravitational basin that extended far beyond the local group and even beyond nearby clusters. The reconstructed flow did not point randomly. It pointed consistently. It aligned with independent measures of motion, including those derived from the cosmic microwave background. Different lines of evidence reinforced one another. At this point, the picture was clear enough to be uncomfortable. There was a region exerting a significant pull on our local universe, and it lay in a direction already suspected from earlier clues. It was not directly visible. It did not announce itself with light. But it left a signature that could not be ignored. Motion had been mapped, the basin had been outlined, the influence was measurable. All that remained was to decide what to call it. By the late 20th century, the evidence had become difficult to ignore. Galaxies were moving together. Their motion was coherent, directional, and persistent. Velocity field reconstructions pointed toward the same region again and again. Yet when astronomers looked directly in that direction, the sky offered very little in return. It was from this tension between motion and visibility that the Great Attractor emerged. The name did not come from a dramatic image or a spectacular discovery. It came from necessity. Astronomers needed a way to refer to the gravitational influence that appeared to dominate the motion of galaxies in our part of the universe. Whatever it was, it exerted a measurable pull. Whatever it was, it lay largely hidden from view. And whatever it was too significant to remain unnamed. Calling it the Great Attractor was not a declaration of certainty. It was a label for a problem that had become well defined. One of the key figures involved in clarifying this picture was Norman Dressler. Through detailed studies of galaxy clusters and their motions, Dressler and collaborators helped demonstrate that the observed flows could not be explained by known nearby structures alone. Their work contributed to the growing realization that a massive concentration of matter lay in the direction indicated by velocity measurements. The estimated mass involved was staggering. Early calculations suggested a mass equivalent to tens of thousands of large galaxies, concentrated across a region of space tens of millions of light-years wide. Later refinements adjusted these numbers, but the conclusion remained the same. This was not a minor perturbation. It was one of the most massive structures in the local universe. Importantly, the Great Attractor was never proposed as a single object. It was not a supermassive black hole. It was not a giant galaxy lurking unseen. It was not a point-like source of gravity pulling everything inward. Instead, it was understood as an extended region of enhanced mass density, spread across a large volume of space. This distinction matters. The word attractor can be misleading. In everyday language, it suggests a destination, a point that objects fall toward. In dynamical systems, the term is more subtle. An attractor is a region toward which trajectories tend to evolve over time. It does not have to be a single location. It does not have to be sharply defined. In this context, the Great Attractor refers to a gravitational basin, a broad region where matter density is higher than average, creating a gradient that influences the motion of galaxies over enormous distances. Galaxies drift toward this region not because they are aiming for it, but because gravity shapes the flow of space around them. This metaphorical use of the term is important to keep in mind. The Great Attractor is not pulling galaxies in like a vacuum cleaner. It is shaping their motion in the same way a valley shapes the flow of water. No single drop is targeted. The landscape does the work. The spatial extent of this region reinforces that point. Estimates place the core of the Great Attractor at roughly 50 to 70 million light-years away, with its influence extending far beyond that. It is embedded within a network of clusters and filaments, not isolated from them. Its boundaries are fuzzy by necessity, defined by influence rather than edges. Nearby galaxy clusters feel this influence clearly. The motion of clusters such as those in the Hydra and Centaurus regions aligns with the flow toward the attractor. These clusters are massive in their own right, yet their collective motion reveals that they are part of something larger. This is one of the strongest arguments for inferred dominance. Individual clusters have strong internal gravity, but when entire clusters move together, responding to a shared pull, the cause must be correspondingly large. The Great Attractor does not overpower local gravity. It adds to it, subtly redirecting motion over time. What makes this especially compelling is the consistency across independent lines of evidence. Velocity field reconstructions, bulk flow measurements, and the dipole seen in the cosmic microwave background all point toward the same general region. Each method has its own uncertainties, each has its own limitations, yet they converge. That convergence is what gives the Great Attractor its standing. It is not based on a single observation or technique. It is supported by a web of indirect evidence that reinforces itself. At the same time, astronomers have been careful not to oversell the idea. The Great Attractor is not treated as a finished explanation. It is a working concept, refined as new data become available. Its mass estimates have shifted. Its exact location has been adjusted. Its relationship to surrounding structures has grown more nuanced. Scientific caution is essential here. Inference-based discoveries carry a special responsibility. Because the object itself is not directly visible, every assumption must be scrutinized. Every conclusion must be tested against alternative explanations. This caution is evident in how astronomers talk about the Great Attractor today. It is not described as a mysterious force or an anomaly that defies understanding. It is described as a region of enhanced mass density, whose influence is measured through motion. Ordinary physics applied on extraordinary scales. There's also an important correction built into the modern view. The Great Attractor is not necessarily the final destination of local motion. It may itself be part of an even larger structure. Its influence may overlap with others. In a universe shaped by a cosmic web, no basin exists in isolation. This layered structure complicates simple narratives, but it aligns beautifully with what simulations predict. Mass gathers hierarchically. Smaller structures sit within larger ones. Influence accumulates rather than concentrates cleanly. From this perspective, the Great Attractor is both significant and incomplete. It marks a region where gravity clearly matters, but it does not represent the end of the chain. It is one feature in a landscape that extends far beyond what can be mapped directly. There is a quiet restraint in this conclusion. Astronomers resist the temptation to turn the Great Attractor into a singular explanation for everything. Instead, it is treated as a slough, a signpost pointing toward the deeper structure of the local universe. Gentle humour occasionally enters the discussion, often aimed at the name itself. The Great Attractor sounds dramatic, even ominous, but the reality is far more patient. Nothing is rushing. Nothing is falling. Galaxies are drifting, responding to gravity with all the urgency of a continental shift. That contrast is part of what makes the concept so compelling. The name suggests drama. The physics delivers subtlety. What ultimately matters is not whether the Great Attractor can be photographed in full detail. What matters is that its influence is measurable, repeatable, and consistent with known physical laws. It earns its place in cosmology, not by how it looks, but by what it does. In this sense, the Great Attractor represents a milestone. It shows how far cosmology has moved beyond relying solely on light. Motion, inference, and structure now work together to reveal aspects of the universe that would otherwise remain hidden. The Great Attractor is not a monster lurking in the dark. It is a region of space doing what gravity has always done, quietly shaping motion across vast distances. Its importance lies not in mystery, but in confirmation. Confirmation that motion tells the truth, even when light does not. For a long time, astronomers drew maps of the universe the way one might draw a city map at night. Bright places were marked clearly, dim regions were sketched lightly, empty areas were often left blank. Structure was defined by where light appeared strongest. That approach worked, up to a point. Clusters of galaxies were identified by proximity. Superclusters were described as loose groupings of clusters that seemed to sit near one another in space. Boundaries were drawn based on where the light thinned out, or where galaxy density dropped below a convenient threshold. These maps were useful, but they carried an unspoken assumption. That structure is best defined by where things are. As motion measurements improved, that assumption began to feel incomplete. Galaxies that looked close together were not always moving together. Others, separated by large distances, shared the same drift. It became clear that proximity alone did not capture how the universe was actually organized. Something more fundamental than position was shaping cosmic relationships. This realization led to a different way of thinking about structure, one based not on static location, but on motion. One of the clearest expressions of this shift came with the introduction of the Laniakea supercluster, a structure identified and described through the work of Brent Tully and collaborators. Laniakea is not defined by sharp edges or visible walls of galaxies. It is defined by flow. The name itself reflects that idea. Laniakea means immense heaven, a poetic nod to scale rather than shape. It refers to a vast region of space, hundreds of millions of light-years across, within which galaxies share a common flow toward the same gravitational basin. This is what makes Laniakea different from earlier supercluster definitions. Traditional superclusters were often collections of clusters that appeared close together on the sky or in three-dimensional space. Their boundaries were fuzzy but still drawn primarily from density maps. Laniakea, by contrast, is defined by motion. If galaxies are moving toward the same region, they belong to the same structure, regardless of how far apart they may appear. This is known as flow-defined geography. In this framework, a supercluster is not a static object. It is a drainage basin. Galaxies flow inward along the cosmic web, guided by gravity toward regions of higher mass density. The supercluster is the area over which that flow converges. This idea reframes how gravitational basins are understood. A basin is not a container, it is a region of influence. Its shape is defined by trajectories rather than borders. Where flow lines diverge, one basin ends and another begins. These divisions are real, but they are dynamic rather than rigid. Because gravity operates continuously, these boundaries are not fixed forever. As mass redistributes and structures evolve, flow patterns can shift. Over cosmic time, the geography of the universe changes, slowly and subtly. This is why Laniakea does not have a neat outline. Its edges are defined statistically by identifying where galaxy motions stop converging toward the same region and begin flowing elsewhere. In some directions, this transition is sharp. In others, it is gradual. The universe does not provide clean lines for convenience. Placing the Milky Way within this picture is both humbling and clarifying. Our galaxy sits well inside the Laniakea supercluster. Along with the rest of the local group, it participates in the same large-scale flow. The Milky Way is not drifting randomly through space. It is moving as part of a coherent region defined by shared gravitational influence. Within Laniakea, the Great Attractor occupies a central role. It lies near the bottom of the basin toward which much of the surrounding motion converges. This does not mean it is the center in a geometric sense, nor does it mean everything will eventually pile up there. It means that, within this region of the universe, the gravitational gradient points broadly in that direction. Seen this way, the Great Attractor becomes easier to contextualize. It is not an isolated anomaly. It is a feature within a much larger structure. Its influence is significant locally, but it exists as part of a hierarchy of mass concentrations that together shape the flow of galaxies across Laniakea. This hierarchical view resolves many earlier confusions. Instead of imagining galaxies being pulled toward a single hidden object, astronomers now see them moving along interconnected pathways, responding to overlapping basins of attraction. Motion is guided, not commanded. One of the most striking aspects of flow-defined geography is how it reorganizes cosmic neighborhoods. In traditional maps, galaxies might be considered neighbors because they appear close together. In flow-based maps, neighbors are those that share a destination. Two galaxies separated by tens of millions of light-years can belong to the same supercluster if their motion is aligned. Two galaxies that appear adjacent may belong to different basins if their flow diverges. This redefinition feels counterintuitive at first. Human intuition prefers fixed boundaries and visible landmarks, but gravity does not recognize those preferences. It responds to mass, wherever it lies, and motion reflects that response faithfully. There is also a practical benefit to this approach. Flow-defined structures are less sensitive to observational gaps. Even when parts of the sky are obscured or poorly sampled, motion upstream and downstream can constrain the overall pattern. Structure emerges from consistency rather than completeness. This is particularly important near the plane of the Milky Way, where direct observation remains difficult. Flow-based mapping allows astronomers to incorporate indirect evidence naturally, without inventing features where data are missing. The result is a map that feels more alive. Instead of static points connected by arbitrary lines, the universe becomes a landscape shaped by currents. Galaxies move the way rivers flow, guided by terrain that is mostly invisible but entirely real. There's a gentle elegance to this picture. It reduces drama without reducing meaning. Nothing is racing, nothing is collapsing catastrophically. The universe is simply following gravity's contours, slowly and persistently. It also reframes humanity's place within the cosmos. The Milky Way is not central, special, or stationary. It is a participant in a much larger pattern. Our cosmic address is not defined by coordinates alone, but by motion. We live in a region of space that flows toward a particular gravitational basin, alongside countless other galaxies doing the same. Maps based on this idea look very different from traditional star charts. They emphasize arrows over dots, trajectories over positions. They tell a story of influence rather than appearance. They reveal relationships that are invisible in static images. This does not make older maps wrong, it makes them incomplete. Light shows where matter is. Motion shows what matter is doing. When the two are combined, structure becomes clearer than either alone could provide. Laniakea represents one of the clearest successes of this combined approach. It is not a structure that could have been identified by brightness alone. It emerged only when astronomers took motion seriously as a defining property of the universe. In that sense, Laniakea is less a thing than a way of seeing. It marks a shift from thinking of the universe as a collection of objects to understanding it as a system of flows. Galaxies are no longer just occupants of space, they are participants in a shared gravitational environment. This perspective continues to reshape cosmology. As velocity measurements improve and surveys expand, new basins and boundaries will likely be identified. The cosmic map will be redrawn, not by adding more dots, but by tracing more paths. The universe does not organize itself for our convenience. It organizes itself through gravity, and gravity, given time, leaves patterns that motion is uniquely suited to reveal. In Laniakea, those patterns come together into a coherent whole, a vast flowing region of space, defined not by what it looks like, but by where it is going. By the time astronomers began mapping large-scale motion and gravitational basins, one conclusion had become unavoidable. The matter that shines is not the matter that dominates. Most of the mass shaping the universe does not glow, sparkle, or announce itself in any obvious way. It does not emit light, reflect it, or absorb it strongly. Yet its influence is written everywhere in motion. This unseen component is known as dark matter. The idea itself is older than many people realize. In the 1930s, the Swiss astronomer Fritz Zwicky studied the Coma cluster, a massive collection of galaxies bound together by gravity. By measuring how fast those galaxies were moving, he calculated how much mass would be required to keep the cluster from flying apart. The result was unsettling. The visible galaxies did not contain nearly enough mass. The cluster should have dispersed long ago if only stars and gas were involved. Zwicky concluded that there must be large amounts of unseen matter providing the necessary gravitational glue. He called it dark matter, not as a metaphor but as a literal description. It was matter that could not be seen. At the time, the idea was largely set aside. The data were limited, and the concept felt speculative. But as decades passed, the same problem appeared again and again, in different contexts at different scales. This became known as the mass discrepancy problem. When astronomers measure how fast stars orbit within galaxies, they find that outer stars move far faster than visible mass alone can explain. When they measure the motion of galaxies within clusters, the same shortfall appears. When they study gravitational lensing, where mass bends light from distant objects, the bending is stronger than luminous matter can account for. In every case, gravity behaves as though far more mass is present than can be seen. The solution that emerged was not a single exotic object, but a pervasive component of the universe. Dark matter is thought to make up the majority of all matter, outweighing ordinary matter by roughly a factor of 5. Stars, planets, gas, and dust together form only a small fraction of the total mass budget. This perspective is formalized in what is known as the lambda cold dark matter model, often shortened to lambda CDM. It is the current standard framework for understanding how the universe evolves on large scales. In this model, ordinary matter plays an important role, but dark matter dominates gravity. Cold in this context means slow-moving, not hot. Dark matter particles, whatever their nature, move relatively slowly compared to the speed of light. This allows them to clump efficiently under gravity, forming structures early in the universe's history. Lambda refers to dark energy, which governs the accelerated expansion of space, but on smaller scales, dark matter sets the stage. One of the most important features of dark matter is how it organizes itself. Rather than forming stars or compact objects, dark matter settles into vast halos. Every large galaxy is embedded in an extended halo of dark matter that stretches far beyond the visible disk. These halos overlap, merge, and interact, forming the backbone of the cosmic web. Visible matter follows this structure. Gas falls into dark matter halos, cools, and forms stars. Galaxies light up the densest regions of an otherwise invisible framework. In this sense, galaxies are tracers. They mark where dark matter has already gone. This explains why dark matter dominates gravity. Gravity depends only on mass, not on brightness. If most of the mass resides in dark halos, then those halos dictate how galaxies move. Stars contribute to gravity locally, but their influence fades quickly with distance. Dark matter halos extend much farther, shaping motion on much larger scales. Dark matter also clusters differently from ordinary matter. Gas and stars can collide, heat up, and lose energy. Dark matter does not appear to do this, at least not significantly. It interacts primarily through gravity. This allows it to form diffuse extended structures that remain stable over billions of years. Because it does not radiate energy, dark matter does not collapse into compact objects the way gas does. Instead, it forms smooth halos with gently varying density. These halos provide the gravitational scaffolding upon which visible structures assemble. This behavior is critical for understanding large-scale motion. The gravitational basins identified through velocity field mapping are not carved out by stars alone. They are shaped overwhelmingly by dark matter. The Great Attractor, for example, cannot be explained without invoking enormous amounts of unseen mass. The luminous galaxies in that region contribute, but they are only the visible peaks of a much larger mass concentration. The true attractor is the dark matter distribution underlying those galaxies, It is this invisible mass that generates the gravitational gradient guiding the motion of surrounding clusters. This connection is one of the strongest pieces of evidence for dark matter's reality. The Great Attractor is not detected through light, but through influence. Its existence is inferred because galaxies move as though it is there. Remove dark matter from the picture, and the motion no longer makes sense. There is a temptation to think of dark matter as something exotic and unknowable. In practice, its behavior is remarkably consistent. It follows clear rules, it clusters predictably, its effects match simulations with impressive accuracy. What remains unknown is its microscopic nature, not its macroscopic role. This distinction is important. Astronomers do not invoke dark matter casually. They rely on it because it works. It explains multiple, independent observations using a single, coherent framework. Alternatives have been proposed over the years, but none have matched dark matter's explanatory power across all relevant scales. Dark matter's invisibility is not a weakness of the concept. It is part of its definition. If it emitted light, it would already be classified as ordinary matter. Its invisibility forces astronomers to rely on inference rather than direct detection. This reliance has proven surprisingly robust. Gravitational lensing maps trace dark matter halos directly through their effect on background light. Galaxy rotation curves reveal dark matter's presence within individual galaxies. Large-scale simulations reproduce observed structure only when dark matter is included. Motion studies, like those leading to the identification of the Great Attractor, demand its influence. Each line of evidence reinforces the others. There's also a useful humility embedded in this approach. Dark matter reminds astronomers that the universe does not organize itself to suit human senses. Vision is not a privileged pathway to truth. Gravity is equally valid and often more revealing. Gentle humour occasionally creeps into discussions of dark matter, often in the form of understatement. Astronomers will sometimes note that dark matter is invisible, abundant, influential, and completely indifferent to our attempts to see it. It does not hide. It simply does not glow. The dominance of dark matter reframes how structures like the Great Attractor are understood. The attractor is not a collection of bright galaxies exerting an outsized pull. It is a region where dark matter density is especially high, with luminous matter merely outlining its shape. This also explains why such structures can be difficult to map directly. Dark matter does not respect the boundaries of optical surveys. It does not align neatly with what telescopes reveal. Its distribution must be reconstructed through motion, lensing, and statistical inference. In this sense, the Great Attractor is a triumph of indirect science. It demonstrates how much can be learned without direct detection. By trusting gravity and motion, astronomers can map mass that remains forever dark. This does not mean detection efforts are unimportant. Experiments continue to search for dark matter particles directly, but the cosmological evidence does not depend on their success. Dark matter has already earned its place through what it explains. The universe moves the way it does because most of its mass is invisible. Galaxies drift along paths shaped by dark halos. Clusters fall toward regions of enhanced dark matter density. Superclusters form where dark matter accumulates most strongly. Motion, structure, and gravity all trace the same unseen framework. The Great Attractor is one expression of that framework. Not an anomaly, but an expected consequence of how matter is distributed when most of it cannot be seen. In the end, dark matter's dominance is not mysterious in its effects. It is quiet, steady, and predictable. It does not announce itself with light, but it leaves no ambiguity in motion. Inference once again proves sufficient, even when detection remains out of reach. As evidence for large-scale flow accumulated, something interesting happened. Agreement grew, but unanimity did not. Astronomers largely accepted that the motion of nearby galaxies could not be explained by local gravity alone, and that a significant concentration of mass lay in the direction indicated by velocity measurements. What remained open to discussion was the nature of that mass. Was it concentrated in a single dominant region, or was it spread across a broader, more distributed landscape? This question sits at the heart of competing interpretations surrounding the Great Attractor. It is not a dispute about whether motion exists or whether gravity is responsible. Those points are well established. The debate concerns how best to describe the underlying structure producing that motion. One interpretation treats the Great Attractor as a relatively concentrated basin, a region where mass density peaks strongly enough to dominate local flow. In this view, surrounding structures contribute, but one area plays a leading role in shaping the motion of nearby clusters and groups. An alternative interpretation suggests a more distributed picture. Instead of a single dominant attractor, the motion may result from the combined influence of several large mass concentrations spread across a wide region. In this view, the flow is not converging on one place so much as responding to a gradient formed by overlapping structures within the cosmic web. Cosmological simulations play a crucial role in exploring these possibilities. When large volumes of the universe are simulated under gravity, starting from early conditions inferred from observations, they naturally produce flows that resemble what is seen locally. Sometimes these flows point toward a dominant basin. Other times, they reflect the combined pull of multiple structures arranged along filaments. Importantly, both behaviors are expected outcomes in a universe shaped by dark matter and hierarchical structure formation. Simulations do not insist on a single answer. They show that reality can be messy without being chaotic. Observational uncertainty is a major reason this debate persists. Mapping motion requires knowing distances, and distance measurement in astronomy is famously difficult. Astronomers rely on what is known as the distance ladder, a chain of methods that extend outward from nearby objects to the far reaches of the observable universe. Each rung on this ladder carries its own uncertainties. Small errors at one level propagate upward, affecting everything that follows. When distances are slightly off, inferred velocities change. When velocities change, reconstructed flows shift. Type 1a supernovae play an important role in this process. These stellar explosions have remarkably consistent intrinsic brightness, making them useful as standard candles for estimating distance. By comparing how bright a supernova appears to how bright it is expected to be, astronomers can estimate how far away it is. However, even this method is not perfect. Dust can dim light. Intrinsic variations exist. Calibration depends on nearby measurements that carry their own uncertainties. When Type 1a supernova distances are used to infer peculiar velocities, small errors can translate into noticeable shifts in flow reconstructions. This is where error propagation becomes critical. An uncertainty of a few percent in distance can lead to a significant uncertainty in velocity once expansion is subtracted. Over large samples, these uncertainties can blur the precise location of inferred attractors. As a result, different studies sometimes identify slightly different centers of flow. Some reconstructions place the dominant influence closer to one cluster. Others distribute it across several regions. These differences are not contradictions so much as reflections of data limitations. Alternative flow centers have been proposed over the years, often linked to nearby superclusters, or extended filaments within the cosmic web. In many cases, these centers overlap significantly. The disagreement is often about emphasis rather than existence. This nuance can be lost outside the scientific literature. It is tempting to frame the debate as competing camps, one advocating a single attractor and another denying it entirely. In reality, the difference is more subtle. Most astronomers agree that there is a major mass concentration influencing local motion. The question is how sharply defined that concentration is. Survey limitations also play a role. Even with infrared and radio observations, parts of the sky remain difficult to map in detail. Distance measurements are unevenly distributed. Some regions are well sampled, others are sparsely covered. This unevenness can bias reconstructions toward better observed areas. As surveys expand and improve, some of these biases are reduced, but none are eliminated entirely. Cosmology often advances by degrees rather than leaps. Confidence grows gradually as independent methods converge. It is also worth noting that disagreement is not a flaw in this process. It is a feature. Competing interpretations force assumptions into the open. They encourage better data, improved methods, and clearer definitions. Where uncertainty exists, debate keeps it visible rather than buried. In this case, the debate has already produced valuable outcomes. It has refined models of large-scale flow. It has improved distance calibration techniques. It has clarified how sensitive velocity reconstructions are to underlying assumptions. Perhaps most importantly, it has encouraged restraint. Astronomers are careful about what they claim. The Great Attractor is not presented as a singular, perfectly defined object with known boundaries and mass. It is described as a region of influence whose exact structure is still being refined. This caution reflects the complexity of the problem, not weakness in the evidence. There is also a growing sense that multiple interpretations may be compatible. A distributed mass concentration can still produce a dominant flow direction. A primary basin can still be embedded within a larger gradient. These views are not mutually exclusive. From the perspective of the cosmic web, this makes sense. Structure is hierarchical. Small basins sit within larger ones. Influence overlaps. Motion responds to the total gravitational landscape, not to neatly isolated features. Seen this way, the Great Attractor is less a single answer and more a useful description. It captures the fact that our local universe is being guided by mass concentrations beyond what can be seen directly, without insisting on a level of precision the data cannot yet support. This approach reflects a mature scientific attitude. Where evidence is strong, conclusions are firm. Where uncertainty remains, language softens. Models are treated as provisional, not final. There is a quiet confidence in this restraint. The motion of galaxies is not in question. The role of gravity is not disputed. The presence of large-scale structure shaping that motion is well supported. What remains open is the fine detail. As new surveys come online and distance measurements improve, these details will sharpen. Flow reconstructions will become more precise. Boundaries will be better constrained. Some interpretations will be favored over others. Until then, the debate continues, not as a sign of confusion, but as a sign of health. In cosmology, certainty is earned slowly. The universe does not yield to simple descriptions. It rewards patience, comparison, and a willingness to accept partial answers. The competing interpretations surrounding the Great Attractor reflect this reality. They do not undermine the concept. They refine it. And in doing so, they keep the science honest, grounded, and appropriately cautious, even as the picture grows clearer with time. When astronomers talk about galaxies being pulled towards something, It is easy to imagine gravity acting in a familiar way. Objects fall inward, distances shrink. Eventually things arrive. On cosmic scales, that intuition breaks down. To understand why, it helps to return to general relativity, the framework that governs gravity at the larger scales. In this picture, gravity is not a force pulling objects through static space. It is the result of mass and energy shaping space and time themselves. Objects move along paths determined by that curvature. Crucially, the space they move through is not fixed. The universe is expanding. Space between distant galaxies is stretching, carrying objects apart even as gravity works to draw them together. These two influences operate simultaneously, and neither can be ignored. Motion on large scales is always the result of their competition. Gravity tries to deepen valleys in the cosmic landscape. Expansion steadily raises the floor. On small scales, gravity wins easily. Stars orbit within galaxies. Galaxies remain bound within clusters. Distances are small enough that expansion is negligible compared to gravitational attraction. The universe behaves in a way that feels intuitive. On larger scales, the balance changes. As distances increase, the effect of expansion grows stronger. Space itself stretches, adding separation over time. Gravity still acts, but it must work against an ever-expanding background. The result is not collapse, but drift. This is why attractors, like the Great Attractor, are never actually reached. Galaxies are influenced by gravitational basins, but the expanding universe prevents simple infall. Instead of falling inward along straight paths, galaxies approach asymptotically. They move toward regions of higher mass density, but their motion slows relative to the expanding space around them. The destination recedes even as they move. Asymptotic motion is a subtle idea, but an important one. It describes motion that continues indefinitely without completion. The path has direction, but no endpoint. The influence is real, but it does not result in arrival. This is not a failure of gravity. It is a consequence of scale. Over cosmic timescales, expansion and gravity reach a kind of uneasy coexistence. Gravity shapes local structure and guides motion along filaments and into basins. Expansion prevents those motions from collapsing the universe into a single dense state. The two influences balance in a dynamic way, producing the large-scale patterns observed today. Long-term trajectories in this environment are gentle and drawn out. Galaxies drift over hundreds of millions of years, covering distances that feel enormous, yet remain small compared to the total size of the universe. Their paths curve slowly, shaped by overlapping gravitational influences rather than dominated by any single source. This means that motion should not be imagined as a race toward a finish line. There is no moment when a galaxy reaches the Great Attractor and stops. There is no collision waiting at the end of the journey. The flow is continuous, not terminal. Cosmic timescales reinforce this perspective. The universe is billions of years old, and its future stretches billions of years ahead. Changes that feel dramatic on human timescales are barely perceptible in this context. Even substantial gravitational influences act patiently, reshaping motion over spans that defy everyday intuition. This patience is why non-collisional outcomes dominate large-scale dynamics. Galaxies rarely collide directly. Clusters interact and merge slowly. Most motion involves gradual redirection rather than sudden impact. The universe prefers slow persuasion to abrupt confrontation. It is tempting to frame motion in terms of destinations because that is how human movement works. Travel implies arrival. Journeys end. Goals are reached. On cosmic scales, Motion is better understood as response rather than pursuit. Galaxies respond continuously to the gravitational landscape they inhabit. That landscape itself evolves as matter redistributes and space expands. Nothing stands still long enough to serve as a final destination. This reframing removes much of the drama often associated with cosmic attractors. There is no impending fall, no looming collision, no sense of inevitability in the human sense. The Milky Way is not on a collision course with a hidden object. It is drifting along a gradient, shaped by gravity and expansion together. Seen this way, the Great Attractor is not a place the Milky Way is going to. It is a feature of the terrain the Milky Way is moving through. This distinction matters because it aligns expectation with reality. Motion without arrival is not unsettling once it is understood properly. It is simply how an expanding universe behaves when gravity is present. There is also a quiet elegance in this balance. Expansion prevents gravity from dominating completely. Gravity prevents expansion from erasing structure entirely. Together they produce a universe that is neither static nor collapsing, neither chaotic nor rigid. The equations of general relativity describe this interplay precisely, but the intuition can be grasped without mathematics. Space stretches, mass curves it, motion follows from both. No single influence has absolute control. As a result, large-scale motion never resolves into rest. It continues, guided but unfinished. Galaxies flow along filaments, into basins, and through regions of varying density, always adjusting, never concluding. This perspective also explains why measuring motion is more informative than predicting endpoints. Since there is no final arrival, the value lies in understanding direction, coherence, and influence rather than destinations. Motion reveals structure. It does not promise resolution. Over time, the paths of galaxies may change subtly as expansion accelerates and structures evolve. Some flows may weaken, others may strengthen. The cosmic web itself will slowly stretch and thin, but the basic principle remains. Gravity guides, expansion carries, motion continues. Removing destination framing brings clarity. It strips away unnecessary drama and replaces it with a more accurate picture. The universe is not pulling everything toward a single point. It is shaping motion through a complex, evolving landscape. The Milky Way's journey, if it can be called that, has no finish line. It is part of an ongoing process that has been unfolding for billions of years and will continue long after any human timescale loses meaning. In this context, asking where the Milky Way is going becomes less about arrival and more about influence. Not where it will end up, but what is shaping its path right now. Gravity and expansion together provide the answer, not as a destination, but as a continuous drift through a universe that is always in motion. By the time the Great Attractor enters public conversation, it often arrives carrying unnecessary baggage. The name alone invites dramatic interpretations, and when paired with incomplete explanations, it can give rise to ideas that sound far more alarming than the science supports. One of the most common misconceptions is that the Great Attractor is a black hole. This idea is understandable. Black holes are familiar symbols of extreme gravity, and the phrase attractor suggests something powerful and consuming. But the comparison breaks down almost immediately once the physics is examined. According to black hole physics, a black hole forms only when matter is compressed beyond a very specific density threshold. Mass must be packed into a region small enough that not even light can escape. For objects with the mass of stars, this region is tiny. For objects with the mass of galaxies, it is still relatively small on cosmic scales. The Great Attractor does not meet these conditions in any sense. Its estimated mass, while enormous, is spread across tens of millions of light-years. That mass density is far too low to produce a black hole. In fact, it is lower than the average density inside many galaxy clusters that are perfectly ordinary and stable. Gravity depends not just on how much mass exists, but on how concentrated that mass is. A black hole requires extreme concentration. The Great Attractor is the opposite. It is diffuse. This distinction matters because gravity behaves very differently in these two cases. Black holes dominate their immediate surroundings, producing dramatic effects only at relatively short distances. The Great Attractor influences motion gently and collectively over vast regions of space, without any sharp boundary or point of no return. Another misconception swings in the opposite direction. Some descriptions portray the Great Attractor as a void, a kind of empty region that galaxies are somehow falling into. This idea is equally incorrect. Voids do exist in the universe. They are large, underdense regions where relatively little matter is present. Galaxies tend to move away from voids toward denser areas, but this does not make voids attractors. They are defined by absence, not accumulation. The Great Attractor is associated with excess mass, not a lack of it. The motion of galaxies points toward increased density, not emptiness. Confusing the two reverses the physics entirely. Media exaggerations have not helped. Headlines sometimes frame the Great Attractor as a mysterious force pulling everything toward doom, or as a hidden monster lurking behind the Milky Way. These narratives are catchy, but they miss the point. There is no danger associated with the Great Attractor. Galaxies are not being dragged toward destruction. The Milky Way is not on a collision course. Nothing dramatic is going to happen as a result of this motion, now or in the distant future. The scales involved are too large, the timescales too long, and the forces too gentle. The Milky Way's motion toward the Great Attractor is measured in hundreds of kilometers per second, which sounds fast until placed in context. On cosmic scales, this is a slow drift. It unfolds over hundreds of millions of years. Even over the entire lifetime of the universe so far, the resulting displacement is modest relative to intergalactic distances. This is why danger narratives collapse under scrutiny. Gravity on large scales does not behave like gravity near compact objects. It organizes motion without violence. It persuades rather than overwhelms. At the scales relevant to the Great Attractor, gravity is remarkably ordinary. That may sound disappointing, but it is one of the most important points to understand. The Great Attractor does not require exotic physics. It does not violate known laws. It does not demand speculative explanations. It emerges naturally from the same gravitational principles that govern everything else in the universe. What makes it seem strange is not what it is, but how it is detected. Humans are deeply visual thinkers. We trust what we can see. When something influences motion without appearing clearly in images, it feels mysterious. In reality, this is simply a consequence of how mass and light behave differently. Much of the mass in the universe does not emit light. This has been known for decades. The Great Attractor is one of many regions where dark matter dominates the gravitational landscape. Its invisibility is not exceptional, it is typical. There is also a tendency to anthropomorphize cosmic motion. Words like pulling, falling, and heading toward suggest intention or urgency. They imply a beginning and an end. On cosmic scales, these metaphors mislead more than they help. Galaxies are not falling toward the Great Attractor in the way objects fall on Earth. They are responding to a gravitational gradient within an expanding universe. Their motion is continuous and unending, shaped by overlapping influences rather than directed to single target. This is where intuition often struggles. Everyday gravity feels decisive. Drop something and it hits the ground. Large-scale gravity feels indecisive by comparison. It nudges rather than commands. It shapes motion slowly, over distances that make final outcomes irrelevant. The ordinariness of the Great Attractor at scale is what makes it scientifically valuable. It is not an anomaly, it is an example. It shows how structure forms, how mass distributes itself, and how motion responds to that distribution in a universe dominated by dark matter and expansion. Seen this way, the Great Attractor becomes less of a headline and more of a case study. It demonstrates that even the most influential structures can be understood without invoking extremes. No singularities, no catastrophes, just gravity doing what gravity does when given enough space and time. This perspective also reinforces a broader lesson in cosmology. Scale changes everything. Phenomena that feel dramatic on small scales become gentle on large ones. Forces that feel overwhelming nearby become subtle when spread across millions of light years. The Great Attractor feels dramatic only because its name and invisibility invite the imagination to run ahead of the physics. Once the numbers are examined and the mechanisms understood, the drama dissolves. What remains is calm motion. Galaxies drifting along filaments, clusters responding to overlapping gravitational basins, the Milky Way participating quietly in a flow that has existed for billions of years and will continue for billions more. There is no urgency in this motion, no climax, no resolution waiting just ahead. The universe is not pulling us toward anything special. It is simply shaped the way it is, and motion reflects that shape faithfully. Returning to calm framing is not about downplaying significance. It is about aligning language with reality. The Great Attractor matters not because it threatens, but because it teaches. It shows how much can be learned from motion alone, and how little spectacle is required for something to be important. Understanding this replaces fear with familiarity. The unknown becomes the merely unseen, the dramatic becomes the ordinary, and the Great Attractor settles back into its proper role, not as a cosmic menace, but as a quiet feature of a universe that behaves exactly as gravity says it should. The question that began this exploration was a simple one, at least on the surface. Where is the Milky Way going? It feels like a question that should have an answer shaped like a destination, a place on a map, a point in space, somewhere toward which everything is moving. What emerges instead is something quieter and far more honest. The Milky Way is moving. That much is not in doubt. Its motion has been measured in multiple ways, using different techniques, instruments, and assumptions. Against the cosmic microwave background, our galaxy carries a clear velocity. Relative to nearby galaxies, that motion aligns into a shared drift. When averaged across large volumes, the flow becomes coherent rather than random. This motion is not inferred casually. It is built from decades of careful measurement, redshifts corrected for expansion, distance estimates refined again and again, velocity catalogues expanded and cross-checked, flow fields reconstructed statistically rather than imagined visually. This is the domain of observational cosmology, a discipline grounded in the idea that the universe must be understood as it is measured, not as it is expected to be. It is patient work. It values consistency over spectacle. It advances by ruling things out as much as by proposing explanations. From that work, several conclusions stand on firm ground. Galaxies do not simply ride along with cosmic expansion. On top of that expansion sits a pattern of motion shaped by gravity. That motion is coherent across vast distances. It cannot be explained by local interactions alone. It reflects the influence of large-scale structure. The Milky Way participates fully in this flow. It is not special. It is not exempt. Along with its neighbours, it moves as part of a larger region defined by shared gravitational influence. That region has been mapped, not by drawing boundaries in space, but by tracing the paths galaxies follow through it. The Great Attractor emerges from this picture not as a singular object, but as a useful description. It marks a region where mass density is high enough to shape motion across much of our local universe. Its influence is inferred rather than directly seen. Its mass is dominated by dark matter rather than light. This much is known with confidence. What is also known just as clearly is what remains uncertain. The precise distribution of mass in that region is still being refined. Distance measurements, though vastly improved, carry unavoidable uncertainty. Flow reconstructions depend on assumptions that are reasonable but not perfect. Obscured regions of the sky continue to limit direct observation. Even the language used reflects this caution. Astronomers speak of basins rather than centres, of flows rather than falls, of influence rather than attraction in the everyday sense. These choices are not evasive. They are accurate. There is no single point toward which everything is heading, no final location waiting to be reached. This is where honesty matters most. The universe does not owe clarity where clarity cannot yet be earned. Observational cosmology does not fill gaps with certainty for the sake of a cleaner story. It allows unresolved questions to remain visible, precisely because pretending otherwise would distort what is already understood. One of those unresolved aspects is scale. Structures overlap. Basins sit within larger basins. The Great Attractor itself appears to be part of an even larger arrangement of matter. Motion responds to the total gravitational landscape, not to neatly isolated features. Another uncertainty lies in the future. Expansion continues. Dark energy shapes the long-term behaviour of space itself. Over immense timescales, the balance between gravity and expansion will evolve. Flows may weaken. Structures may drift apart. The patterns observed today are not frozen in place. What does not change is the nature of the motion itself. It is ongoing. It has no end point. It is not leading toward a collision or a climax. Galaxies drift along gradients that shift slowly over billions of years. Direction exists without destination. Influence shapes motion without completing it. This reframes the original question in a subtle but important way. Asking where the Milky Way is going implies arrival. The better question is what is shaping its motion right now? And that question has an answer grounded in measurement rather than metaphor. Gravity, distributed across large-scale structure, guides the drift. Expansion ensures that the drift never resolves into collapse. Dark matter dominates the mass that matters most. Light traces only a small fraction of what shapes motion. Taken together, these facts describe a universe that is dynamic but not dramatic, active without urgency, structured without rigidity. There is a quiet satisfaction in this picture. It does not rely on extremes. It does not demand spectacle. It explains motion using the same physics that explains everything else, applied patiently across immense scales. Following the drift does not lead to a revelation waiting just ahead. It leads to understanding that settles slowly rather than arriving suddenly. The scale of the universe does not rush. It unfolds. The Milky Way moves. It has always moved. It will continue to move, not toward something singular, not toward an ending, but along a path defined by gravity, shaped by structure and carried forward by an expanding universe that does not pause for destinations. The motion does not conclude, it simply continues, and that quietly is the answer.